Anyway, we're here at 2:41, so we're into our start time. Any remaining questions? Okay. Announcements. So, well, first of all, we have our warm-up question. And normally this would be review from last time, but I've fallen far enough behind that it's not. And this one is actually meant to be a challenge question. So it's review and challenge for material that you haven't seen yet. So if you all fumble on this one, don't feel bad. We'll get back to it a little bit later in the lecture. And if we need to, we'll put you in break rooms, discuss, and we'll try again. But anyway, I'm going to put it aside for a little bit. Announcements. Here we are on the Cengage WebAssign site, and you can see I've postponed homework 1 till Wednesday, in part because I'm behind, either just me getting used to this new format or the computer problems I've been having, but also a lot of you are scrambling, trying to leave campus this weekend, so I didn't want it to be due Friday or Monday. I had already shifted it to Monday, but now I've shifted it to Wednesday. And I'm pretty sure that's not going to shift again. But so, keep that in mind. Wednesday is when you want the homework done. Don't put it off to the last minute is my recommendation. And you can see homework 2 is now visible, and we'll get to that when we get to that. I think that's the only announcement for today. So last time we were talking about the seasons. Let me go back to the doc cam. Yeah, so we were talking about the seasons. Actually, let me put up this slide in the background here. Come back to that as well. And why is it hotter in summer and colder in winter? And we concluded it's not a proximity effect for various reasons I won't repeat, but it has everything to do with the tilt of the Earth. And because of this tilt, there are 2 effects. 2 things that affect how warm your place on the planet gets. And so let's write them out. And I kind of started talking about the first one a little quickly at the very end of class, but let's write out both of these effects and what they depend on and explore them a little bit more thoroughly. The first one is the directness of the illumination. How direct is the illumination? And the second one is the duration of the illumination. So the more direct it is, it's more intense heating, and the longer it is, you get more heating as well. So both of these come into play. Now, directness of illumination, that's supposed to be an N, depends on something we call the horizon angle. Let's write what each of these depend on or what they're related to. So the horizon angle, this is just the angle that something is above the horizon. Here we're talking about the horizon angle of the sun. This is at midday. The horizon angle of the sun changes all day. When it's rising or setting, that angle is 0. So you got to pick kind of a common time so you can compare from day to day. And we pick midday. And we define that not as noon, but as when the sun is highest in the sky, which is usually a little bit after noon. And during daylight savings time, it's another hour beyond that. And so horizon angle of the sun in the sky, how high it is in the sky affects the directness of the illumination. I'll demonstrate that again. And the other one, we'll get to duration of illumination. And this depends on the fraction of Earth that is illuminated. And this is at your particular latitude. This fraction varies depending upon the latitude that you're talking about. Okay, let's tackle directness of illumination first. And let me just demonstrate that using my flashlight here. Maybe I'll turn off the light there on the doc cam. I'm afraid to touch the doc cam now because I'm pretty sure it's what's causing my blue screens. But anyway, here I have a flashlight. The flashlight's going to represent the sun. this down here is the ground. And so here's an example of direct illumination. The sun is directly overhead, and it's casting, the flashlight casts a certain amount of energy, and it's casting it into a small area. So that's a lot of energy per unit area. It's concentrated. So if you're in that area, you're going to warm up more quickly. Though sometimes at midday the sun isn't here, but it's down at a lower angle. We'll see this is the case in the winter months. And when it's at a lower angle, you see that energy is spread out over a larger area. Same amount of energy, but spread out over a larger area, so it's less energy per unit area. So if I'm living somewhere in here, I'm getting a lower concentration of light, and I'll heat more slowly. So directness has a big effect. It's all about that horizon angle. This is a high horizon angle. This is a low horizon angle. Okay, I think next I want to go back and demonstrate this on our globe light apparatus. And I'm going to cautiously rotate my dot cam around because this is when I died in the last class. There we go. And then I flip it and flip it. Okay, so let me go over there. Okay, so here we are. This is our sun. This is the Earth. And we're in the summer configuration in the north, the winter configuration down below. As we talked about before, as the Earth orbits the sun, the tilt stays fixed in three-dimensional space. At least over the time scale of a couple years, it doesn't change that much. We're, of course, spinning once a day. We orbit once a year, and the tilt stays fixed as we go. Now, what we're trying to do is connect directness of illumination to horizon angle. Let's take North Carolina. Here it is. And I'm going to point it towards the sun. I'm on the edge of my UNC blanket here. It's tipping it a little bit. But point it towards the sun. That means it's midday in North Carolina. And again, it's summer in the northern hemisphere. We're clearly getting very direct illumination. So this should be a very high horizon angle. I'm going to use this thing to measure the angle. I think it's technically has suction cups here. I think it's for drawing circles on a whiteboard, but you know, it's what I have, so it's what we'll use. And I'm going to put this on North Carolina flush with the globe. And what this represents is our local horizon. So let's say here's a person standing on North Carolina. This would be their northern horizon. That would be their southern horizon. And with this one here, I'm going to make it flush with the table. The table is the ecliptic, the plane of the solar system. In other words, that's pointing towards the sun. It's a little confusing because the sun's a little bit lower here. I guess I could lower it and match it to the sun. But just remember, the sun in reality is very, very far off in that direction. So this little change here doesn't matter that much. Anyway, the point is, this is, let me do it a little bit more carefully, something around there. This is how high the sun gets in the sky in North Carolina, midday, first day of summer. It's not directly overhead. That 90 degrees would be directly overhead. It gets pretty high in the sky. It's up to about 80 degrees. I think it's like 78 degrees for Chapel Hill. So it gets high in the sky, pretty direct illumination, straight down on us, but not directly overhead. Now let's go to winter. So we're going to orbit around the sun. And I'm just going to peek around my second monitor. Yep, you're all still there. Now, I could have another computer problem, and you all disappear, and I would just keep talking here for who knows how long before I realize you're not there. So I check every now and then. Let's get North Carolina pointed at the sun again. Okay, but now it's winter, so the light is spread out across the higher part of the globe that we're now in. Again, I'll put this on North Carolina. There we are. So this is standing straight up, northern horizon, southern horizon. And you can see, if I make this flush with the table, that's a lower angle. So first day of winter at midday, the sun only gets that high in the sky, or something like this. And this is something you've probably noticed, that the sun is high in the sky in summer, around the middle of the day, and it's lower in the sky in winter. But if you haven't, maybe you noticed it in the back of your mind, but now this is something you'll never miss again. And I'm going to give you an exercise where you're going to go out and observe this over the course of the semester, observe the change. So these kinds of things you maybe kind of noticed subconsciously maybe, we're going to move them to the forefront of your mind. Well, anyway, that's North Carolina. Let's look at some edge cases. Let's take a look at the Arctic Circle. So, you know, more extreme cases. The Arctic Circle starts, well, it is 23.5 degrees below the North Pole. 23.5 degrees because that's the tilt of the Earth. Earth's tilted 23.5 degrees. So if I come 23.5 degrees down, it's flush. This is my local horizon. And again, this is first day of winter in the Northern Hemisphere. So the sun, the angle there is 0. The first day of winter in the Northern Hemisphere, and which is first day of winter. If I'm on the Arctic Circle, that means the highest the sun gets in the sky at midday is the horizon. And so for the other 24 hours, it's beneath the ground. We don't see it. It comes up and just barely skips the horizon and down again. So it's mostly dark with just a glimmer of twilight. Now, as I move higher up, that circle the sun's making on the sky is even lower. It's beneath our horizon, so we don't see it at all. Imagine going to the North Pole. There's our horizon right there. And if I try to take this leg and point it at the sun, I can't. It would have to go through itself and through the globe. Basically, the sun would be 23.5 degrees below the horizon. And so you never see it if you're above the Arctic Circle, if you're at the North Pole in particular, for the first day of winter. And for an extended period of winter, the higher up you go. Okay, let's go back to the other side. So back to the summer configuration in the north, winter in the south. And let's keep considering the Arctic Circle. I'll put North Carolina pointed towards the sun again. And the Arctic Circle is about here. So in summer in the Northern Hemisphere, the sun at midday does have an appreciable angle. It's up in the sky. It's not North Carolina up in the sky, but it's still up in the sky. And we can go all the way to the North Pole, actually, and it's still up in the sky. So during summer, if you can get above the Arctic Circle, the sun's up all the time. In fact, if we go to the nighttime side of the planet, let's go back down to the Arctic Circle. That's this horizontal point right here, 23.5 degrees down on the back side. So this is around midnight. And there the angle is 0. So when it's summer in the Northern Hemisphere here, and we're on the Arctic Circle, that means the sun is up all day and it just barely glances, skims across the horizon, and then is up again. That's something I've never witnessed. I've always wanted to go up above the Arctic Circle in summer and just watch the sun do a loop around the sky and have 24 hours of sunlight. I guess it would also be interesting to see the 24 hours of darkness in winter, but I'm less inclined to go up and check that out myself. Okay, come back around here. All that makes sense? Was that helpful visualizing it? Okay. Let's see what's next in terms of our figures. So this was all about directness of illumination. Again, here's just another example of that. The next thing we want to talk about is fraction of illumination. So here I have, this is from another textbook that we don't use. I have some globes here, and I try, it helps for your understanding if everything is always oriented the same way. And so far, the globe has always been tipped to the other direction, so I kind of semi-flip this using my massive Microsoft Paint skills. Microsoft Paint's my favorite program, so we'll see lots of examples of my skills with this ancient piece of technology. Anyway, I flipped it around, but I couldn't flip the continents how they're drawn. So it looks a little weird. Don't worry so much about that. But let's look at the geometry and some of the labels here. So this is summer in the north, winter in the south, and here on the other side of the sun, winter in the north, summer in the south, just like the demo we just saw. And some of these lines we recognize. There's the equator, Arctic, Antarctic circles, but this also throws in the Tropic of Cancer and Tropic of Capricorn. And these are 23.5 degrees away from the equator. The only thing that makes them special is on the first day of summer, Tropic of Cancer, right here, the sun is directly overhead at midday, like directly, 90 degrees up. That's that one special place on the planet where it does pass directly overhead. And for the Tropic of Capricorn, same deal. Summer in the southern hemisphere, that's directly overhead, 23.5 degrees below the equator. Anyway, that's not the reason, that's the definition of those terms. It's not the reason I put this up. The reason I put this up is you can see what fraction of the globe is illuminated pretty easily. Let's come back over here. Summer in the north. Here's the equator. If you look above the equator, this whole region right here is illuminated. And only this sliver right here is in darkness. So starting at the equator, we have 12 hours of sunlight and then 12 hours of darkness. But as we move our way up, when this is in the summer configuration, we have longer and longer periods of sunlight and shorter periods of darkness. Finally, you get to the Arctic Circle and it's 100% illuminated, like 24 hours a day. Now down in the southern hemisphere, as we move away from the equator, we have longer periods. See, we have a large fraction of the globe in darkness and only a small fraction illuminated. So as we go farther south, when we're in this configuration, the winter configuration in the south, the nights get longer, the days get shorter until you get to the Antarctic Circle and it's 24 hours of darkness. Of course, when we go to the other side of our orbit, everything's flipped. Up here in the northern hemisphere, we have a small fraction illuminated, so short days, long nights. And in the southern hemisphere, it's their summer, a large fraction illuminated, long days, short nights. So this contributes to the heating as well. We've had two effects: directness, the concentration, how much energy per unit area, and now the duration, how long you receive that energy. Both of those impact the temperature of the planet and how it changes with time and latitude. And if you're in the lab course, Lab 2, we dive into this in some detail, so you're going to see it again. Questions about either of those? Okay, let's add some terms. I think that's next. Move the dot cam back. And flip it. Turn the light on. Okay, yeah, we'll do some terms and then we'll go back to the e-polling question. Okay. So let's define terms. Summer solstice, winter solstice, and the equinoxes. So that's going to be vernal and autumnal. Autumnal, that's correct. Equinoxes. The word solstice, equinox, these are very old terms, and we'll encounter them when we do archaeoastronomy in a handful of classes. But in general, what they mean, summer solstice is the first day of summer, and that's true for either hemisphere. First day of summer in the north is around June 21st. Sometimes it's June 20th. And first day of summer in the south is December 21st. So just June 21st doesn't mean first day of summer. That's just in the northern hemisphere. Summer solstice refers to different dates in different hemispheres, something to keep in mind. It's the first day of summer. It's the, as we now understand, it's the longest day of the year. And the sun is highest in the sky at midday. So you need kind of a common time to measure that, since the sun's height in the sky changes always from rising to setting, but at midday. Winter, it's just the opposite. This is the first day of winter. It is the, I guess I can write out of, first day of winter. It's the shortest day of year, and the sun is lowest in the sky at midday. Okay, And then we have the vernal and autumnal equinoxes. Vernal is a fancy word for spring. Autumnal, autumn, that of course means fall. And this is when you're partway between these two places in your orbit. So this is the first day of spring and fall, respectively. And what distinguishes this is on the equinoxes, everywhere on the globe, we have 12 hours of day and 12 hours of night. And I'll bring up a figure to illustrate that. So this figure again, here we have summer in the north, so this would be autumn in the north, spring in the south, and winter in the north, and so over here it's spring in the north, fall in the south. And if you look at the globe at these positions, the tilt is neither towards the sun nor away from the sun. And so it's going to be 12 hours of day, 12 hours of night anywhere on the globe. Just imagine being at a certain part of the globe here, you rotate around for 12 hours and then 12 hours on the other side. I just did the equator. So at the equator, it doesn't matter where you are in the orbit. It's 12 hours a day, 12 hours of night on the equator everywhere. But the special thing about the equinoxes is even if I'm way up here near the Arctic Circle, half of it's in darkness and then the other half of the globe is in light. So 12 hours everywhere. Same over here on the vernal equinox. 12 hours and then 12 hours on the backside. And again, it's because the tilt is neither toward nor away from the sun, so it's a simple 12-12 division everywhere. Okay, given that, let's go back to our warm-up question and see how you did. You just have to remember where I put it. Here it is. Okay, and I'll read through it, and then you can put an answer in if you haven't yet, or if you did put one in before, it got reset when no, that was the last class, so it's good. If you put it in before, it's there, and if you haven't yet, you can put something in. Which of the following has the longest period of daylight? Northern Hemisphere summer on the Tropic of Cancer, anytime on the equator, the equinox anywhere on the Earth, or Northern Hemisphere winter on the Antarctic Circle. Let's go ahead and put in some answers. I'll give you another 10 or 15 seconds, and then we'll see how you did. We have about 75 of you here today, so hopefully we can get a few more answers than that. See if we can push it up to 50, and then we'll take a look. .48's pretty close. You can keep answering if you want to, but let's take a look at some of the answers, at all of the answers. So this is what we got. I see a lot of ones, some twos and threes, a good number of fours. Let's look at the histogram here. So most of you answered 1, and 1 is not the correct answer. So as your punishment, I'm going to put you in break rooms. Let me see. I did this for the previous class, so I think I figured it out. Break rooms. And let's see. We have 75 of you. Maybe if I want, maybe we'll do 20 break rooms. There'll be 2 to 3 people per room, and you've been put into those break rooms automatically. So go there, and after about 20 or 30 seconds, I'm going to close the room, and that gives you, I think, a 60-second counter before you'll come back. I'll reset the question, and feel free to submit a new answer, 2, 3, or 4. We know it's not 1, but go talk it out in the break rooms. Oh,
can
1
you put
second.
the question to the front of your screen so that we can see it before we go to the break room?
I'll do that, and once you're in the break rooms, I don't know if you still see the screen share. I haven't established that yet, so you may want to do a quick screen capture.
I don't know if there's a way to do it, but I haven't seen that happen yet in my other classes.
Okay.
Yeah, you can't see the screen share if we break out into breakout rooms. So just take a picture of it like on your phone or something. That's
Okay.
what I usually do.
Yep, take a picture, and then I'm going to open the rooms right now, and you all can go in there. So once you come back, go ahead and resubmit your solution. Okay, I think everyone's back now. So let's see how you did. I'll give you a second to get your answers in there. We had 48 of them last time, so we should have at least that many this time. So tell me how that worked. For most of you, was there another person in your break room, or did some of you end up there by yourself effectively?
I was alone, so I just came back.
Okay. Maybe I'll put more people in the rooms next time.
A ton of people also like left right whenever you said break rooms. So like 20 people left.
Yeah, people don't like to socialize, so strange. All right, let's take a look at our answers. Yeah, this looks better. Well, someone's still insisting it's 1. They're really adamant, but most of you got it. The answer is 4. So let's figure out why this is here. I'll put both of these under the dot cam at the same time. So the first one was Northern Hemisphere summer on the Tropic of Cancer. So Northern Hemisphere summer is this configuration, Tropic of Cancer. And you can see it's going to be more than 12 hours. It's 12 hours down here at the equator. It's more than 12. Turns out to be about 13 and a half of daylight, and the rest is night. So, okay. anytime on the equator. In the equator, it's always 12 and 12 during the summer, during winter, and any time in between. Equinox, anywhere on Earth, as we just discussed, that's the point in the orbit where it doesn't matter where you are on Earth, since the tilt's not towards the sun or away. It's 12 hours a day, 12 hours a night. The last one, that was the challenge part of this. It's not a trick question. I never give trick questions, but this is the challenge. It's a challenge question. Challenge to see if you really understand the terminology. Northern Hemisphere winter, so we're talking about this, but when it's winter in the Northern Hemisphere, I'm asking you to consider the Antarctic circle, not the Arctic circle. The Antarctic circle's down here, and there you can see it's 24 hours of day, because it's their summer when it's our winter. I think y'all get that now. Okay, cool. Last thing I'm going to mention here is the ground's eye view. So we've talked about this from what it, how it looks from above. This kind of a God's eye view where you see the whole system. But that's not how we normally view the sky. We're not out there in space looking back upon things. So what does this look like from the point of view of the ground? I'll describe this, and then I'm going to assign you an exercise to do. So here's a person standing in a field. We have north in this direction, south in this direction. And let's start with the equinox. The equinox, the sun rises due east. It comes up in the sky. It doesn't pass overhead because we're in the northern hemisphere. And so that means the sun's a little bit towards the south. We're above the plane of the solar system, so we have to look towards the south. So it goes across our southern sky, sets due west. Now, let's say the sun's over there. In summer, the Earth is tipped towards the sun, so the sun will be higher in our sky. It will rise north of east, spend a long time up in the sky, and then just a little bit of time below ground, sets north of west. Again, if the sun's over there, for our winter, our hemisphere is tipped away from the sun. So the sun is not high in our sky anymore, but low in our sky. Rises south of east, spends just a little bit of time up, sets south of west. So in this diagram, you can see the horizon angle at midday is higher in summer, lower in winter. The length of day is longer in summer, shorter in winter. And so for your exercise, what I want you to do is go to, it's in the ebook under lesson 1. This is a semester-long exercise. So I went to seasons. Down here, it's written out, and there's a worksheet that comes with it, and there's the worksheet. I want you to go out about once a week and try to observe these things. So in this column, put the date. In this column, estimate how high the sun is in the sky. And just do it real roughly. If the sun's over there, that's 0 degrees. 90 degrees is straight up. There's 45, there's 60, there's 35. Block the sun with your hand. Now, don't look directly at the sun. Don't look directly at the sun. And for third time, for legal reasons, don't look directly at the sun. So I'm safe now. But block the sun with your hand, and then just kind of measure that angle. And, I'll ask about this stuff on exams. I'm not going to ask, was it 67 degrees or 68 degrees? The questions would be like, was it 30 degrees or 60 degrees? And you can get that kind of accuracy just eyeballing it using your arm and your eye. The other thing I want you to do is estimate the time of sunset. When does the sun set? And you can look this up online, or you can actually go out on this day and try to see when it goes below the horizon. Now, if it's daylight savings time, mark it here. So to get length of day, if it's not daylight savings time, just double the sunset time. If the sun set at 6 p.m., double it, 12 hours approximately, good enough. If daylight savings time, you have to subtract an hour off before you double. So in daylight savings time, if it sets at 7, take 6, double it, and that's 12. Okay, questions about seasons?
I had a question about the worksheet. So we do estimate like the agreed above the horizon at like midday, right? Okay.
Yep, yeah, at midday. Of course, it changes throughout the day, so this will be at midday. Okay, cool. Let's jump into our next topic. We might be able to finish it today, which would be great. And the next topic is precession. Let me get a fresh sheet here. I'll write the term. Precession. And so this is to correct a lie I told you. Though when I told you the lie, in fairness, I qualified it. But I'm going to turn the dot cam around. Again, hope I don't lose everybody. So far, so good. Back up here. A little higher so my head's not cut off. And I'm going to flip it and flip it. Okay, precession. So, we've talked about daily motions, the Earth spinning on its axis once a day. We've talked about annual motions or orbit around the sun. This is a much, much longer term motion. And the lie that I told you is that our axis stays fixed in space as we go around the sun. It's always tilted the same way, no matter where we are in the orbit. And that's not true. It actually changes very slowly. Precesses, that's the term. So here we are in the summer configuration in the northern hemisphere. And when I come around, since this is changing very slowly, and I'll talk about the reasons why, but it's going in this direction. So as I go around, the orientation the tilt changes, I'll hit summer a little bit early. If the tilt stayed the same, I'd have to come all the way to here to have summer. But since it's changing this way, by the time it comes around, it will have tipped a little bit, and I'm pointed towards the sun a little bit earlier. Now, I'm exaggerating how much. It's a really small effect, barely noticeable, but we hit summer 20 minutes earlier each day. And so the next year, it'll be here, the next year it'll be here, the next year it'll be here, until eventually we hit summer over there, and this side of the orbit is winter. Now, it takes 13,000 years to go halfway around, from summer being here in the orbit to winter being here in the orbit, and summer being there, and then another 13,000 years to get back. So it's a 26,000 year cycle. Now, I should point out that we don't really notice this because our calendar is designed to compensate for this. Right now it's hot. The summer begins, it's hot. First day of summer is in June. And by the time we get over there, the first day of summer will still be in June because the calendar is designed to accommodate these 20 minutes. So it's always, the Earth pointed towards the sun happens at the same time in our regular calendar. But what changes is where it occurs in the orbit. Okay, so that's precession. But why do we have precession? And the best way to get a feel for this is to get a feel for tops, because the mathematics of Earth precessing is exactly the same as the mathematics of a top. So have you all played with tops before? Yeah. Probably my experience with tops comes from growing up half Jewish and playing with dreidels during Hanukkah, gambling for pennies. Sadly, that's kind of the extent of my religious education, gambling for pennies during Hanukkah. But anyway, so I play with tops, and let me bring up a slide to go with that. Here's your standard top. And tops, they spin on their axis, but the axis also, it's spinning on the axis like this, but the axis also slowly precesses, changes its direction, slower than the rate at which it's spinning. Now, for a top to do this, the dot cam back up. For a top to do this, there are two factors that matter. The first is the top non-spherical? The technical term is aspherical, where A means non. If your top is a perfect sphere, the mathematics, the physics of it, it does not precess. So aspherical. And the second thing you need is a force acting on the top. If the top is out there spinning in space, it maintains its orientation. You have to have some force for it to precess. And we won't work through all the physics, but I'll just demonstrate it. So I have a rather fancy top, like a $100 top. Now I'll put it under the dot cam and we can all watch it here. That's the base. Here's the top. Technically, it's something called a gyroscope. And it has this kind of spherical frame, but all the mass is this disc here, which you can see is It is a disk, it's not a sphere. And I'll put it on here at some angle once I get it spun up, and we should be able to see it precess. Now I have to really spin it up a lot faster than I can with my hand. So there's a little motor here. Let me connect it. Okay, it's accelerating. I don't know if you can hear that, but I can hear that. I'll let it get a little bit faster. Okay, now detach it. I'll turn that off because it's loud. And it's trying to process in my hand. It's weird. It's like jumping around. I'll put it with a certain tilt there and let go, and it doesn't fall over. It's processing. So the top part is spinning inside really, really fast. It's processing more slowly. And the speed at which it processes depends on how aspherical it is and what force is acting on it. In this case, it's the force of gravity pulling downward. Now there's friction, so it's losing energy, and it's tipping over more and more as it does. And at some point, it will hit the little rubber bumpers and fall off, and it's my job to catch it before it falls on the floor, because it's like a $100 top, and I'm not sure why the physics department lets me use it, but there we go. And it's still trying to wiggle in my hand, and I'll just slow it down without giving myself a burn there. So that was the top view of the top. I also have a little movie here of the top in case you didn't quite understand it from looking at it from the top of the top. It's the exact same model. So this is what I saw from the side, just spinning around like that. Okay, so that's how tops work. Earth, it's the exact same deal. Now you may think Earth is not aspherical, Earth is a sphere, but it's not a perfect sphere. And that's because it's a rotating body. Maybe I'll draw it here under the dot cam. So here's Earth, but it's spinning on an axis. And that causes the middle to fly out a little bit. This is greatly exaggerated. It's like being in a car going around a track or going around a curve really quickly. You're thrown to the outside. So the equator is moving the fastest. It has to cover the greatest distance in the same time. So it feels that force and it's pushed to the outside. So Earth is actually a little bit wider along the equator than it is pole to pole. A smidgen, you can't notice it by looking at a picture, but it's there. So we're a little bit aspherical, which means we will precess just super, super slowly. And indeed, we spin once a day on our axis, but we'll precess over, as I said before, 26,000 years, very, very slowly compared to our spin rate. Let me see here. And in this case, the force isn't like the top sitting on the table. Here, the forces are provided by the sun and the moon. But you work through the mathematics, and it's exactly the same as the top. One observable of this, we don't really know where we are in our orbit, and our calendar is designed to compensate for this, so it's not really observable in terms of time and season, but it's observable in terms of the pole star. Look at the rotation axis of Earth. The rotation axis points to the North Celestial Pole. That's the definition of the North Celestial Pole. And if we change the orientation by a lot, the tip is 23.5 degrees. So changing it over to here, that's a 47-degree difference in the sky from one side to the other. It means the pole star will change tremendously. So this yellow circle shows where in the sky the rotation axis is pointed, where the North Celestial Pole is. But nowadays, it's really close to Polaris, so we call that the pole star. But in the future, maybe this star, and then that star, and that star, none of them are exactly on the circle, but you just grab the brightest star on it, or close to it, and call that the pole star. You got a really bright Vega over here, so in about, 12,000 years, we'll think of Vega as the pole star, although it's not as close as Polaris is at the moment. You have long swaths of time where nothing is the pole star. Working backwards in time, maybe about 3000 BC, Thubian was a really good pole star. Not super bright, but right on this circle. So that's a consequence of precession. The pole star changes with time. Okay, that is it for precession. We've talked about rapid daily motions. We've talked about annual motions. Now we've talked about this long precessional motion. Next thing we will do will be to throw the moon into this as well. Phases, lunar months, and then we'll put the sun, the earth, and the moon together and talk about eclipses. We'll pick up with that next time. And I'll stick around for questions. So thanks a lot.
So
Thank you.
how long
Thank
does this
you.
whole circle take to finish, like return to the same point?
The whole loop is a 26,000 year cycle.
Okay, got it.
13,000 to get to the other side, and then 13,000 to get back to the original configuration.
How did they figure that out?
How did they figure that out? Well, the pulsar changes. And, you know, we have recorded records going back quite some time as to, you know, what star to use for north, because, you know, we navigated the sea before that. And so there is good record of the North Celestial Pole moving with respect to stars like Polaris.
Okay.
Very long historical records, but they exist.
Hi, could you possibly explain how precession relates onto seasons again? I don't know if I think I heard you say that.
Right, yeah. So since Earth's axis, its rotation axis is changing, we hit our seasons 20 minutes earlier than we would have if this were not occurring. Now, the beginning of summer is defined as when the rotation axis is pointed towards the sun. And since the orientation of that axis is changing, we hit that point in our orbit 20 minutes earlier each day. So when I was doing my demo and I had the summer off to the left and winter off to the right, it's not always that way. The first moment of summer inches its way around the orbit until 13,000 years later, summer's on that side of the orbit. 13,000 years later, it's back to this side. And so, you know, the seasons start 20 minutes earlier, but we don't notice it because we've designed our calendar to subtract those 20 minutes as well. So even 13,000 years from now, the first day of summer will be June 21st. We'll just be on the other side of the orbit when it happens.
Did you say 20 minutes earlier per day?
Oh, I meant per year. I'm sorry.
Okay.
I hope I
Thank
didn't
you.
say that throughout the whole lecture. If I did, my
I
bad.
think you did.
Oh, well. It's 20 minutes earlier per year.
Okay. Thank you.
Why is that like important, or like why does that matter?
Why does anything in astronomy matter? So there are very few, I mean, if you want to be philosophical, there's very few real world practical applications coming out of astronomy, some of them. The goal here is just to have a better understanding of how, in this course, the solar system works, and overall between Astro 101 and 102, how the universe works. So we're starting out with just the basics of how the Earth moves, the sun moves, the moon moves, and the celestial sphere, and the primary motions. Now, it did matter for navigation a long time ago, because if they navigated off of Polaris back in 3000 BC, they would go astray. They needed to use Thubian back then, for example.
Okay.
I just wanted to ask real quick. I remember, because you talked about us filling out that seasons worksheet, and I remember last class you mentioned there was another thing in WebAssign that you particularly wanted us to look at, and I didn't write it down.
Yeah, so that, and you can find that was under motion of the celestial sphere. If you go there in the WebAssign ebook, which is just a collection of notes, down the exercises, it describes what to do. It's basically drawing a sketch of the northern sky, drawing a sketch of the southern sky, coming back a few hours later, drawing those sketches again, and really seeing the motions of the stars that we're talking about. It's one thing
Okay.
to understand it intellectually, but it's another thing if you can connect it to your own observations.
Yeah, perfect. Thank you so much. I just wanted to write it down because if I don't, I'll forget it. Thank you so much.
My pleasure.
Wait, what was your question?
Yeah.
Go ahead, Christopher. I think you were first.
Okay. I'm actually in your 120 class, but I like to stay for the second lecture because I like to see things twice.
Yeah, it's usually
But
better the second time anyway, so.
it's a little smoother the second time,
Yeah,
and there's less people. But I was talking to a few people about maybe forming a small little homework group where we went and did the field activities together. And I was just wondering if that's actually a permissible thing to do, or if it would be
yeah,
considered.
absolutely. Hell, the homeworks, I suggest you work on them together in small groups. I don't want like 100 people doing a Zoom session and doing it together.
No way, no way. It would be very small and like
Yeah.
masked and socially distanced and
Yeah,
stuff.
that was the next thing I was going to say. Of course, a lot of people are going home now, and so it's going to be a smaller pool. But
Yeah,
absolutely.
there were a few locals who expressed interest in it, so I thought I'd check.
And you can always put that stuff in the chat board. I can't read the chat comments while I'm managing everything else during class, so I normally don't read through them. But you're welcome to put that up. It looks like a lot of students watch that and comment or at least read them.
Yeah, they definitely do. Sometimes it gets a little out of hand.
Another reason
but-
why I'm going to look at it. I don't want to know.
It's probably
Thank
best
you.
that you don't, but I appreciate it. Thank you.
Sure. Logan, you were trying to ask a question before as well.
Sorry, my mic wasn't working. For the sake of the worksheet, do we consider midday to be noon or the time directly between sunrise and sunset?
Yeah, it's defined as the time when the sun is highest in the sky. So that's halfway between sunrise and sunset. But it hovers up there, you know, it's like a sine curve. And so for a couple hours, it's going to be at about the same angle, the same horizon angle. And the difference is going to be less than your accuracy of measurement using your arm. So anytime around lunchtime through early afternoon should work fine. I'm not asking you to measure it precisely. I want you to notice the change from the beginning of the semester to the end of the semester.
All right, thank you.
Anyone else? Go ahead. Ria, sorry. I don't hear you, I'm afraid, Ria. It says you're not muted, but I don't have your sound. If you want, let me see, I'll open up the chat, even though I said okay, the chat is open. You're welcome to put the question there.
You might also have the incorrect microphone hooked up to the thing. You just press the drop down thing on the mic button. If you want to check.
Can you hear me now?
Yes.
Okay. Thank you for whoever that was. I already read the chapter, but I have a question on triangulation. Like when I read it in the book, it told me to take like a piece of graph paper and then measure it out. But then like thinking back to like pre-cal or like calculus, I remember like you could take like the cosine or like sine of an angle and then figure out like the measurements. I forgot how to do that, but I don't know if you want to show it right now or maybe like during the lesson.
So the triangulation, yeah, it is covered in chapter 1. We covered in lesson 2. So in the detailed, careful reading assignment, you wouldn't have been asked to read that for another week or so, but totally fine. And for us, it's the concept of parallax. And the nice thing about astronomy is the angles that we're measuring are very, very small, you know, because the objects are so far away. Maybe it has a certain extent, but compared to its distance, it's minuscule. So we get to use the small angle approximation. Which is the physical size of whatever we're measuring way out there in space, divided, the size of it divided by the distance is the angle in radians. You can see this in a calculator. If you take sine of a small angle, it's pretty much the same thing as that small angle, as long as it's in radians.
So like if the baseline is 450, and then you have a 90 degrees angle, this is 450, and then this angle right here is 52 degrees, how would I find this measurement? Like by doing the sine cosine part.
So say it again, say it again.
So like you have a baseline, right?
Yeah.
And it's 450. And it's 450. And then you have your 90 degrees angle.
Okay.
And then this angle right here.
So normally, I'll go to the doc cam. So normally in astronomy, let's say we're looking at this. So instead of thinking about one of them being a right angle, think of it kind of where these two angles are the same. And if this is really far away, those two angles are both close to 90. Now, in this case, this angle here, ignore this, I'm just drawing over it, theta, as a fraction of 360 degrees, is going to be the same as this distance as a fraction of this giant circumference going around this point. And so you can write it as theta over 360 degrees is going to be equal to this, the baseline, divided by the circumference of this giant circle, which is 2 pi times its radius, and the radius is the distance away. This is an equation we will use over and over in the course and over in the lab course. But it is an approximation in that this is, as I've done it here, this is actually a curve. In reality, the objects are arcs. But as long as this angle is small, in other words, if the distances are tremendous, then the difference between the arc length and the length on the circumference is so minuscule we don't have to worry about it. But in reality, there'd be something like a, I think this one would actually be a tangent of this angle, be tangent of this over this times 2 pi. Well, I put it at theta here. Tangent of this over this times 2 pi. No,
Okay.
here. Yeah, there we go. So you put the 2 pi up there and take the tangent of this. This is basically tangent of the angle in radians is the baseline over the distance.
Okay,
But
that makes
you know, this is so close, that's the approximately equal sign to just theta over 360 times 2 pi, that we can ignore the tangent or the sine if we're doing one of those. And so we don't need to deal with the trigonometry in this course because not all the students have had it or are comfortable with it.
Okay. I was just like trying to find a simple way to do it, and that's much simpler.
You'll see it a lot
Thank you.
in lesson 2, and if you're in the lab course, like 4 times in different contexts.
Okay. Thank you.
Any other questions?
No, thank you.
Okay.
Hey, I'm sorry, but can you go over Precession real quick again? My thing was kind of lagging out during that session.
Sure, I can do a real brief, and also, of course, see you, Logan. I post the videos to YouTube within a couple.
Oh, so I can just go look at them?
Yeah, absolutely.
Oh, that's cool. That's cool.
Yeah, it'll take me a couple hours to process the file and get it uploaded, but I usually do it same day. And,
Oh yeah, you did mention that. All right, well, thank you.
Sure, it's in the syllabus. The link's in the syllabus.
All right, you have a good one.
You too.